Now I will begin. Good morning, everyone. My name is Jinwei Lang. I'm a PhD student at Hefei Institute of Physical Sciences, Chinese Academic of Science. What I'm going to present is actually still on its early stage, but I really think our findings so far are worth telling you. The topic of my talk is about how predicting neurostimulation responsiveness with dynamic brain network matters. I will begin my presentation according to the following outline. First, reintroduce. So first, I'd like to give you a bit of background. When we talk about the non-invasive brain stimulation methods, one of the famous is TDCS. TDCS has great potential in clinical, such as improving neurocognitive performance in people with neurological and mental disorders. In addition, the widespread use of TDCS also benefits from its low cost and minimal side effect. But however, the TDCS also notices that the neurostimulation responsiveness from TDCS varied hugely among participants. Our previous work demonstrates that the necessary of pre-stimulation screen by showing that people receiving stimulation could be classified into two heterogeneous groups, the positive responders and the negative responders. The positive responders whose performance was improved by TDCS and the negative responders whose performance was impaired. The neurostimulation responsiveness was predicted by functional lateralization index, which calculated from task-based fMRI, but it might not be suitable for patients. Resting state fMRI contains rich patterns of brain activity, which can be quantified with graph theory and network science, such as dynamic functional connectivity matters. Compared with static matters and dynamic matters, dynamic matters can indicate the flexibility reorganization of brain networks, which might be more useful to predict brain heterogeneity. And also, recent studies spotted DFC matters as powerful neuroimaging markers of neurological and mental disorders. Now, let me move to the schema overview of our method used in this research. It contains 5 steps. Step A, extract the time series strategy. We divided the complete time series into sub-windows through a strategy of sliding window. Step C, detection of dynamic communities through a maximum multi-layer community network algorithm. Step D, calculate the dynamic properties of all nodes in the systems. Step E, the last step, predict neurostimulation responsiveness by several machine learning models. The dataset used in our research contains of 45 young adults, and we can classify the total participants into 2 groups: 28 negative responders and 70 positive responders. Our dataset in the right side, the DM network was selected as our region of interest because it's closely related to the TPJ stimulation effect. The default mode network was classified into 3 subsystems: a dorsal medial prefrontal cortex subsystem, a medial temporal lobe subsystem that contributes to memory-based sense construction, and a set of midline cohorts that are especially involved in processing self-referential information. For the ROI templates, we created a sphere ROIs using the MNI coordinates listed in this table at the right side, with the diameter of 10 millimeters. Here you can see we distinguish 3 different default model network subsystems with both of 3 different colors. What I want to highlight is the dynamic community detection method in this slide. We apply the Low-1 algorithm to the series of ROI correlations metrics calculated at the same length to detect network communities. In addition, I want to emphasize that we use gamma equal to 1 and omega equals to 0.4 for balance between community numbers and node flexibility. In this slide, you can see in our research, we take 4 features to the dynamic network statistics. On the top left, the recruitment feature is obtained by calculating the probability that the nodes within the same subsystems are sent to the same community, which reflects the interaction of regions within subsystem. On the bottom left, the integration feature is obtained by calculating the probability that the nodes within the different subsystems are sent to the same community, which reflects the interaction of regions across subsystems. On the right side, we will see that the nodes are constantly switching from community to community throughout the whole time series. So we can calculate flexibility as the probability that the nodes change its community allocation within the continuous time window. And the promiscuity is used to measure whether a node participates in all possible communities. In this slide, I will show you some of our main results. First, we can find that there are several significant differences on bilateral AMPFC, PCC, PSR, RSP, and PHC for the recruitment dynamic feature in different groups of window length and step size. Second, we compared the effectiveness of dynamic and static network measures in identifying positive responders from negative responders. 5 different machine learning algorithms was selected as shown in the table. For each algorithm, we compared the prediction accuracy for the model using static measures alone, using DFC measures, and using the combination of them, of both. We are convinced that our results show that the advantages of DFC over static network measures was manifested by all 5 modeling approaches, but the model based on decision tree yield inconsistent findings because the decision tree model is only use a small number of trees in classification task, and it might be vulnerable to overfitting. Moreover, we calculated the ranking of features importance in the case of all features mixed and found that among the top 5 features, dynamic features accounted for 4 when applied neural network model. Similarly, results have been seen have been produced by other machine learning models. Then I'll come to my conclusion and discussion. The results suggested that the positive responders different from negative responders in this core and MTL subsystems on recruitment. DFC alone shows advantage over static networks measures by several learning algorithms. For discussion, the dynamic community analysis can computationally consider the rapid interaction among nodes and subsystems. And also, the decision tree model might be vulnerable to overfitting because our sample size is small. Last, our study explores the feasibility of pre-simulation screen program using DFC measures from resting state fMRI. This is an acknowledgement to all our members in my library, and also thanks to the USPC, IHMT, and Science Island. Well, thanks for your attention.
Thank you for your presentation. So we have a question. Can you see the question?
Wait a minute.
Yeah, what do you think that the combination of dynamic and static strategies has a lower performance than the dynamic version?
Because in this research, we use the static methods are too many than dynamic methods. Because we use the all node and we use the balance between the dynamic and the static methods are not balanced. So the combination of dynamic and static strategies has a lower performance than the dynamic version. And we will further to discuss it in the future work. Thanks.